so section 9, limit theorems, as we said last time, are a bunch of theoretical tools that allow you to avoid having to do the epsilon n arguments. Okay, so it's like, first we make you do the epsilon n arguments, and then we give you these tools that say, okay, you can stop doing them. You can stop doing them now. The thing is that sometimes those tools don't work, right? So there are cases where you don't have those tools, and in that case you have to get your hands dirty, right? And so you get down to the hard analysis, so-called. Okay. These things you've probably seen before. So the first one has to do with limits and arithmetic. And so it's the following theorem that says if you have two convergent sequences, suppose you have these two limits, and suppose you have these two sequences. The S sub n's converge to S, the T sub n's converge to T. Then basically everything that you think should happen does happen. For any constant in the real numbers, the limit of a new sequence that you get by multiplying everybody by k, it's just going to be k times the old limit. Okay. In other words, k times the limit. B, the limit of a new sequence formed by taking the sums of the sequences is going to be the sums of the limits, right? The limit of the first guy plus the limit of the second guy, right? Et cetera, right? The limit of the product is going to be the product of the limits. And if the limit of the s's is non-zero, then the limit of the quotient will equal the quotient of limits. So what this says, right? What this says is that you can take your sequence and multiply by a number, and then take the limit of that. Or you can take the limit first and then multiply by the number. Okay. So scaling multiplication, you either can do the scalar multiplication and then go through the limit, or take the limit and multiply by the scalar. You can either add these guys together first and then take the limit, or you can take the limits and then add, right? Here you can multiply these guys together and take the limit, or you can take the limits first and then multiply, right? You can take the quotient and then take the limit, or take the limits and then take the quotient of the limits. Okay, so what this is saying is that the limit commutes with arithmetic operations, right? It doesn't matter in what order you do it, right? You can either do that one first, you can do it this way, or you can do it the other way, right? Right? If you want to get to the bottom of the stairs over there, you can either go down the stairs here and go across, or you can go across and then go down the stairs, right? You're going to end up in the same place. Of course, course, that's not true for everything. You can't just reverse the order of anything and hope that it happens correctly. Okay, but it does here. And you see what's good about this, right? Right, like you can't reverse the order of your underwear and your pants, right? It's not the same thing. Right? You don't. Some things commute and some things don't commute. So don't just commute everything thinking that it works. Okay. Okay, so you see what's good about this. What's good about this? So observe. The limit of x as x goes, I'm sorry. I don't want to say that because we're talking about sequences. Actually, let me. Yeah. So okay. So for example, if we're thinking about Mitchell's problem, which was something like 3n plus something over 7n plus something. I don't remember. So that goes to infinity, right? Then you would say, okay, well, I can, this is the same thing as 3 plus. If I multiply top and bottom by, if I multiply the thing by 1, that's okay. Right? I can multiply this by 1. That's the same as the limit of this 7 minus 9 over n as n goes to infinity.
If we use something like that in this homework, what do we do my thought?
Well, the thing is that you're using a particular result, that the limit of a quotient is the quotient of the limits.
Yeah.
Right? Which is not something that you know yet. Right? Why is that true? That the limit of the quotient is the quotient of limits? Somehow it happens. Yeah, we'll see maybe this class or in the next class why this works, but we don't know this yet. We don't know this yet. I hear quiet profanity. Yeah. Maybe if you want to redo it, hopefully that's okay. Yeah. But you should be using epsilon and arguments.
I think there are some things that we had seen in previous homework assignments, where we've proven, for example, that the limit of Sn times Tn is the product of the limits. I think we showed that in one of the homework assignments.
We showed it if one of these guys converges to 0, but not for both guys. Not in another case. Yeah, if we definitely showed it for if one of them goes to 0. Yeah, if you want to redo it, it's fine. Yeah. Right. Okay. So don't use things that we don't have yet. People wanted to use L'Hopital's rule. We're not even going to get anywhere near L'Hopital's rule in this course. Strangely, you think we're not going to get to L'Hopital's rule, but actually L'Hopital's rule requires something called the extreme value theorem, which is hard to get to. I mean, a little bit hard to get to. We could get it, but anyway. Okay, so back here. So then you would say, okay, okay. So to be completely correct about this, you'd have to prove two things. Right? You'd have to prove that the limit of 1 over n as n goes to infinity is 0. Or you'd have to use a couple things. First, you'd have to prove this, right? Okay. And then what would you say? You would say, by property A, I know that this negative 9 over n goes to 0, right? So you say the limit of 3 plus 1 over n equals the limit of 3 plus the limit of 1 over n, right? Yes.
So we thought that was a convention, like the limit of x over infinity is equal to 0.
But this is not x over infinity, right? This is not something over infinity. This is the limit of 1 over n as n goes to infinity.
I don't think
Right,
we've shown
that's
that
different.
Also,
Have we shown it already? If we have, that's fine. Okay, but I'm just saying, if we want to prove this thing, this is what you need. Okay, this is what you need. This is what you would need. Okay. Okay. You'd have to show this, and then you would say, I know that the limit of a sum is the sum of the limits by property B, right? So by property B, right? And then this is equal to just 3 by star. Okay, and then you do something similar for the bottom. Limit of 7 minus 9n equals the limit of 7 minus, plus the limit of negative 9 over n, again by b, right, which is 7. And then here you would have to use property A, like minus 9 limits of 1 over n by property A, right? Because you have to pull out that negative 9, right? And you get 7 minus 0 by star. Right? And then you put those two together, you say by part D, the limit of the quotient, 7 minus 9n equals 3 over 7. So that's how this theorem is used. Okay. Of course, after you do this for a while, then I'm not going to mind if you just say this equals 3 over 7. Okay. But at the beginning, I think you should probably spell it out to make sure that you see what goes into it, right? It's not just you just say, oh, it's 3 over 7. Actually, there's a lot of work that needs to be, a lot of things need to be proven in order to do that. Okay. Yeah. So like analysis is like slow motion calculus, right? You're you're trying to understand every tiny bit of the work that you're using here. Okay. 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 So let's prove B. Okay. So right, our claim is that so we want to show that the limit of s sub n plus t sub n equals s plus t, right? Where s is the limit of the s sub n's and t is the limit of t sub n's, right? So what does that mean in epsilon n language? It means that given any epsilon, what am I going to say? Somebody just say it for me. Given any epsilon.
N in n such that if n is greater than n, then the absolute value of s n plus t n is minus s plus t in parentheses is less than epsilon.
Right. Okay. Right. That's what we want to show. That we want to show that we can find a capital N with this property. Okay. Right. So like S is here, T is here, S plus T is here. Right. Our first sequence gets close to S. Our second gets close to T, and we want to see that the sum can be made close to S plus T. Okay. So, right. So the idea is pretty straightforward. Right? You say, well, look, the S's are getting close to the SNs are getting close to S, the TNs are getting close to T, so, you know, of course, right, of course the sum is going to get close to S plus T, right? So how do you do it, right? We want, so what we're saying is that given any epsilon, let me introduce some name here. Given any epsilon neighborhood, of S plus T, so it's that little interval, you know, here's S plus T plus epsilon, S plus T minus epsilon. So this little interval of radius epsilon is called an epsilon neighborhood. Given any epsilon neighborhood of this thing, there's a time past which all these sums are within the epsilon neighborhood. Okay. How do we show that? Well, we know that given any epsilon neighborhood of S, we can make the guys within epsilon of S. We can do the same thing for T, right? So, does anybody see how we what we need to do? Right? We can make everybody within epsilon of S, within some epsilon of S. We can make everybody within whatever epsilon we want of T. Right? Maybe it's better to use a different word than epsilon, so I'm going to say alpha neighborhood, beta neighborhood. Okay. We can make everybody within alpha of S. We can make everybody within beta of T. How does that get us to make everybody within epsilon of S plus T? Yeah, Mark.
Epsilon has to be less than alpha plus beta.
Bigger than alpha plus beta, right?
Yeah.
Or rather, you want your alpha plus beta to be smaller than epsilon,
Yeah.
right? Yeah. So yeah, exactly. Right? So just choose, right? So how to do it? Well, given an epsilon, take alpha to be epsilon over 2, and beta to be epsilon over 2. Right? Right. Then, since the S of n go to S, we know there exists a time n1 past which the distance of Sn to S is smaller than alpha. Right? Since the Tn's go to T, we know there's an n2 past which the Tn's are within beta of T. What am I going to say next? We're looking for an n past which Sn plus Tn minus S plus T is less than epsilon. How do I find my n? Don't blurt it out. Don't blurt it out. How do I choose my n? The n that gives me what I want. Think by yourselves for a minute. Okay, talk to somebody nearby, behind you, in front of you. Talk to Marco and Julia. Haley and Mitchell, say something to each other. Like, hello. I think we should get out of here. Say something. I'll go outside and walk around.
So if we take those epsilons and we solve those two little things, right? Because we can say the percent
Okay, what's the answer? How do you, Aria?
I think we want n to be the max of n1 and n2.
Exactly. So let n be the max of n1 and n2, right? Because then both of these things is going to happen, right? These guys going to be will be within epsilon over 2 of each other. These guys will be within epsilon over 2 of each other, right? So then, if n exceeds that, so we need to say one thing. How do these two things help us? Right? We've got these guys are within epsilon 2 of each other. These guys are within epsilon 2 of each other. We want to get this thing smaller than epsilon. We use the
Triangle inequality.
triangle inequality. We see that Sn plus Tn minus S minus T by the triangle inequality is smaller than Sn minus S plus Tn minus T, which is smaller than or equal to, which is strictly smaller than epsilon over 2 plus epsilon over 2, which is epsilon. So past that n, these guys, the sum is close to S plus T. So we can make the sum of the sequences as close to the sum of the limits as we desire. Okay. Okay, let's, any questions? Questions, Marco?
Is there anything else you could say, for example, if the limit is being approached from the top for both S and T, could you say that S plus T is also being approached from the top?
You could, yeah. Right, what that's saying is that, what you're saying, I think, is that, right, if Sn is bigger than or equal to S, and Tn is bigger than or equal to T. No, that's not what you're saying. But, I mean, what you say is true. It's true. Let's do a harder one. Number C, letter C. There's only 7 of this. Let me just get started on it. Okay. So proof of C. We want to show that the limit of the product is the product of the limits as n goes to infinity. In other words, given any epsilon greater than 0, existing n such that if we're past it, the distance of this to this is smaller than epsilon. Okay. Okay. And we know that, right, we know we can make, right, we know that can make Sn within some alpha of S and the Tn within some beta of T, right, as before. Okay, so over here, the way you want to think is like this. Okay, over here we were trying to control this. We were trying to control this, right? Sn plus Tn minus S plus T. right? And really the key point was that we had control over this, and we had control over this, right? We had the control over these two things, and we used it to get control over this using the triangle inequality, right? Everybody agree with that? Right? We have control over these two things, and we were able to work that into here via the triangle inequality, which gave us this, right? And then our individual controls resulted in a control over this thing. Okay, so we're going to try something similar over here, right? We've got control over, again, we've got control over this and this. Okay, and we want to use that to control this thing. Okay, but it's not so evident this time, right? It's not so evident this time. Where is the Sn minus S? Where is the Tn minus T? They're not there. Okay, so you do a little bit of scratch work as before. You say, well, look, Sn, Tn minus St. I want to control that thing using these guys, right? This is the only thing, these are my only tools, right? So what I'm going to do is I'm going to force those tools in there. Okay, I'm going to make it, they're not there, I'm going to put them in there. Okay. I'm going to just say, look, I don't see them, I'm going to bring them in. So I subtract Stn and I add Stn as St. Okay, so they're not there, but that's the only thing I have, so I'm just going to introduce them. Right? Right? And you see what I've done. I now have Tn Sn minus S plus S Tn minus T. Right? So now I've introduced them. This thing is absolute value of Tn times Sn minus S plus absolute value of S times Tn minus T. Okay, so I want, it should be less than or equal to, triangle inequality. Right, so as long as I can find an n past which the above is smaller than epsilon, I'm good. Right? Because as long as I can make this thing smaller than epsilon, then this thing is smaller than epsilon, and that's what we want. Okay. Okay, so so we're going to do this in pieces. The first thing we're going to do it in cases. In case S is non-zero. Actually, if S equals 0, then we already did this in a homework problem. Right? If one of those sequences converges to 0, then we already did it. So I could sort of be cheap and say done in homework. Maybe that's what I'll do. Okay, case S not equal to 0. Okay, so think like this, right? We're trying to get control over this thing, make this thing smaller than epsilon. Well, how can I do it? I can make this thing as small as I want. I can make this thing as small as I want. How small should I make this, the Tn minus T? I want this plus this to be smaller than epsilon. So that's the same, so you notice this, as long as I can make this smaller than epsilon over 2, and this smaller than epsilon over 2, then I'm good. So again, as long as I can make this, then we're good. Right? Okay, so let's look at the lower one here. What should I do to Tn minus T? How small should this be to ensure that this happens? how close must Tn be to t to make this product less than epsilon over 2? Absolute value of s is just a number, like 5. Okay? So make this thing smaller than epsilon over 2 times 5, s, right? Okay. So fix epsilon beta to 0. Since Tn goes to t, there exists an n1 past which Tn minus t is smaller than epsilon over 2 times the absolute value of s.
N1?
Yeah, n1.
Does the n comma or?
So that's an n1. There exists an n1 past which. Okay. Okay. So that will take care of the second part. What about the first part? How close do I have to make Sn to s to ensure that this thing is smaller than epsilon over 2? Well, this is a little bit funnier, right? Would you say I needed to make it smaller than epsilon over 2 Tn, 2 absolute values of Tn? That's trouble because the Tn is changing, right? The Tn changes with time. Okay, so that's not going to work. However, Tn converges. So there is a maximum, there is a bound, m, such that the absolute value of Tn is less than or equal to m for all t. Right. Any convergent sequence, as we said last time, is bounded. Okay. So I know that these absolute values of t sub n's are all smaller than that capital N. Right. So how close do I have to be here? I want the Sn's to be
2 over m. Or less than epsilon over 2 then.
epsilon over 2m, exactly. So so now we say there exists, again, since the Sn converges to s, there exists an n2 such that past which Sn minus s is smaller than epsilon over 2m. Oops, don't need the absolute values. 2m. Right? Again, we take the max. Right? Let n be the max of n1 and n2. Then, if we are past that n, we see that Sn minus St, which equals Sn Tn minus Stn plus Stn minus St, which is smaller than Tn Sn minus s plus S Tn minus t, is smaller than m Sn minus s plus S Tn minus t, which is smaller than epsilon times m over 2m plus epsilon over 2 absolute value of s times the absolute value of s, which is epsilon. So that's the proof that that the limit of a product is the product of the limits. You see why we never did it in calculus class?
Yeah.
Right. Right. The next one about the quotients is even worse. Okay. So look forward to it on Monday.